Okay, so now the seminar is recorded. Hello everyone, welcome to the seminar today. Coming with today is we have our speaker, Professor Yboon Garcia Ramos from the Universidad de Pacífico from Lima, Peru. So Yboon obtains her PhD at IMCA under the supervisions of Mark Lasso and Wilfredo Sosa Sandova in 2007. Since then, she has become an expert in the field of rational analysis and optimization. So I don't know that Yboon has been to Australia or not. So welcome to Australia virtually. And we hope you to attend your talk physically in the near future. So everyone, please join me to welcome her to her talk on the characterizing quasiconvexity of pointwise infimum of a family of arbitrary translation of quasiconvex functions. So Yboon, please take your stage.
Okay, thank you very much. First of all, I want to thank you, the organizers, particularly Vera, for the invitation. The title is quite long, but I only talk about a part of this work. This is a work with Fabián Flores from Universidad de Concepción, Chile, and Nicolas Hadjisavvas from University of Aegean, Greece. We will try to do more or less one introduction at this work, who will be published soon. Now it is accepted, so let me fix the framework first. So normally X will be a binary space. X star the continuous dual. We have the duality pairing. For a function f, we have, as usual, the domain of, the epigraph of f, and also the sublevel sets at high lambda and the strictly sublevel set at high lambda. So this is important because we will talk about convex function and quasi-convex function, so we need that. So it's true that the title is very a little large, so no, it's infimum of quasi-convex, infimum of a quasi-convex function, more or less. But the first motivation was more or less a comparison between convex function and quasi-convex function in a particular case. So we can define the convex function like that. No, we can say that f is a convex function if and only if the epigraph of f is convex. In parallel, we can say that f is a quasi-convex function if and only if all the sublevel set, excuse me for the change the notation, all the sublevel set as a convex set. So no, this is like similar. But we know very well that when we take two convex functions, okay, when we take two convex functions, the sum always is a convex function. But if we take two quasi-convex functions, it's very easy. It's very easy that the sum in general is not quasi-convex. Here is an easy example at R. So it's possible here to write. Okay, I can now write. You can define x squared very well, and this is an increasing function minus x cubed, and the sum is very easy. This is not quasi-convex. So this is a great difference between convex and quasi-convex functions. So we ask when we can guarantee that the sum of two convex functions is quasi-convex. Okay. Also, we have some characterizations, a differential characterization. For example, for the convex function, this is a classical result who say that if f is a lower semi-continuous convex function, if only if its differential is maximal monotone. Here's the classical differential in the sense of convex analysis, of course. Here for the quasi-convex function, we choose the Clark-Rockefeller, but in fact there are many others. The characterization say that f is quasi-convex if f is quasi-convex lower semi-continuous, if and only if the differential is quasi-monotone. Okay, this is the clear differential. So also we can do a comparison. We can compare the two concepts. But what happened with operators? So also is well known that if we take a monotone operator and we take an x star in x star, the sum is a monotone. Of course, this is true that if we take two monotone operators, the sum is monotone. But in the case of quasi-monotone operator, we have this result that say that if for all x star in x star, t plus x star is quasi-monotone, this is equivalent to say that t is monotone. So we cannot guarantee that the sum of two quasi-monotone operators is quasi-monotone. Neither this is more easy. So the question is how to preserve quasi-convexity under summation. This is the first question. There are a natural case where we can preserve the quasi-convexity, the convexity of the sublevel set. That is when you take a f, quasi-convex function, and you take a g, a function to R, from R to R, no decreasing. So in this case, the sublevel set are the same. They are the same. So of course, if this is convex, this set is convex. So this composition is quasi-convex. And in this case, we have this sum is quasi-convex. So this is an easy case. But in other case, so this is a question, what happened in other case? So we introduced two concepts. The first is the concept of quasi-convex family, and the parallel with the operator is the concept of quasi-monotone family. So we start with a quasi-monotone family. So if we have a family A of operators, T, we will call a quasi-monotone family if the operator T with graph, the union of the graph of T is quasi-monotone. Particularly, we say that two operators T1 and T2 will be called quasi-monotone pair if T1 and T2 is a quasi-monotone family, only two. This is two is a pair. And in parallel, we have the definition of family of a quasi-convex family. Okay, so a family of function Fe is called a quasi-convex family if for every A and G who belongs to E and every X and Y in X and set in this set. Excuse me, we have a problem with the mouse. Okay, the following implication holds. Okay, we have that. So if fx at x is satisfies that, so we have that his A and his G. So in particular, we say that two functions will be called a quasi-convex pair if this set is a quasi-convex family. So we have two concepts, one in the family of function, the other one in the family of operator. This is, they are parallel. So what is the first result? The first result is try to relate these two concepts. Okay. So we have this concept here. So the theorem say that if we have two functions, lower semi-continuous, okay, then the pair F1 and F2 is a quasi-convex pair if and only if this pair of side differential, this is the Clark-Rockefeller side differential, is quasi-monotone pair. here we need the two function will be lower semi-continuous function. You know, this doesn't work. The tools in here is this result from Nicolas. This is a result of Nicolas Hadjisavvas. That is more or less mean value theorem for lower semi-continuous function. And this is a result of Lasson de Corbellet and Ose, no? Who give a characterization of the quasi-convexity with a safe differential. So we need both, both we need of the function are, the function is lower semi-continuous. So this is the first result that we think. So we have two family, and for the quasi-convex function, here we have the relationship between the function and the differentials. So after we can ask how big is this? How big is the class of quasi-convex pair or lower semi-continuous functions? So here are more candidates, but here I put only 3. Here are 3 candidates that satisfy the condition. The first, the type 1, is the function that have the function who have a proportionality between the differential, like that. This is more or less to say that the count generated by the differential of the two functions are equal. This is more or less. The another type is that we have two functions, not decreasing, the transformation of the same quasi-convex function, like the first case, the easy case. Okay, and another type is when we have two quasi-convex functions and the R mean and the mean of one with the intersection of the another one is no empty. So here we can see we can see some examples. For example, this example, the first example is the type 3. You remember that the type 3 is the R mean F1 with intersect the R mean of 2. But we have here this function defining R2. We have F1 like that, F2. We have the R mean in both cases are 0, but we take these points, particular points, and it's easy to see that this function is not quasi-convex. Okay, so the type 3 is not a quasi-convex family of functions. But here we have another example. Example is very easy. You see, it's very easy. We have the X is equal to R. We have F1 like that. F2 is F1 X. In this case, we can prove that the union of the differential is a quasi-monotone. It's quasi-monotone, so we have a quasi-monotone pair. But this example is neither type 1 nor type 2. So the class of function that are of family of quasi-convex function is large. Okay, it's large. So, and here, first with how I say, first I try to characterize the sum, but after we realize that there are relationships with a minimum of function. So this is one of the principal, the main result of the work. We suppose that the function f1 and f2 are quasi-convex. Then these assertions are equivalent. So f1 and f2 is a quasi-convex pair. This is the second. It's very interesting. For every lambda 1 and lambda 2 in R, the union of these two sub-level sets are convex. The union is convex, excuse me. And also that is equivalent to say that union of this strictest to level set is convex. Also, this is particularly, we have lambda 1 equal to f1 in x, and here is f2 in x, it's convex. And we have E for every alpha R, this function, this is the minimum of if 1 plus alpha, this is the translation, with f2 is quasi-convex. So it was very interesting to find this result, because we're searching about some first. We have this result that is about the minimum of translation. Okay. So also this theorem is true when we are in any vector space. Here we didn't need a structure. We don't talk about a differential. So okay. So this is in general. And here we can see more examples. For example, here we have this condition. You remember so we have this condition that this intersection is empty. For this function f1, this is the minimum of 0x. The another function is max of 0x. So it's very easy. So they are very easy function. Does the differential are a quasi-monotone pair. But the function mean has no minimum. No, it's minus infinite. And the other don't have. So, but it's easy to see that this function is the sum and the mean are quasi-convex function. So we have another example. This is another one. We consider this function. We can see that the union of two level sets are convex. So we have a quasi-convex pair. And so the minimum of these two functions is quasi-convex. So the family, there are a lot of functions that satisfy this this characterization. So what about the sum? So here there are some consequences for the sum of quasi-convex function. Here we take G is 1 to m. We have the family of we have a family of quasi-convex, so quasi-convex family, excuse me. Then the sum of the minimum are quasi-convex. Okay, this is direct from the another theorem. And also we have another characterization that say that if f1 and f2 is a quasi-convex pair, if and only if, for no decreasing function, h1, h2, this function, here the composition plus this composition is quasi-convex. So this doesn't change anything, the composition with no decreasing functions. So, of course, we know that the sum of convex function is a convex function, but we cannot recuperate this result from our work, okay? The result of the sum of two convex functions is convex, so quasi-convex cannot be obtained with our result. But with some examples, we show that our class of functions for which the sum of quasi-convex function is quasi-convex contain no trivial functions. And also, we can use this for preserve some property, okay? So there are another property, there are preserve and the summation in a quasi-convex family. The first one is about semi-strict quasi-convex. So I recall the definition. F is semi-strict quasi-convex if we have this implication. No, this is quasi-convex, but a little more. We have this. If fx is different to fy, so we have this. This is strictly. This is for below. So the sum of The sum of two semi-strictly quasi-convex functions in general is not necessarily semi-strictly. Okay, we can see this example. The identity, F1 is the identity, F2 is the mean of minus x and minus x. This. We have that these two functions are semi-strictly, but the sum no. So it's also the semi-strictly is easy to lose. But the propositions say that if we have a family, we have F1, F2, Fm, with lower semi-continuous. Here we need lower semi-continuous, semi-strictly quasi-convex. So if this is a quasi-convex family, then this sum is also semi-strictly quasi-convex. So we can preserve this property. Of course, we can ask about the minimum. We cannot preserve the minimum with this property, only the sum. The sum is semi-strictly, but the minimum in general no. Okay, so there are also another family of functions. That is the C family. It was introduced by Suzuki in these words. So here we have a non-empty subset of Rn. We have the syntacticon in the typical way. And it says that F belongs to C if for all x in the domain and all b in this asymptotic conic of domain F. We have one of these property of okay, or this function is not decreasing, or this is plus infinity, like a coercitivity. It's like a coercitivity. Okay. So for example, convex function or coercive function are in C. Okay. We have proof that if we have a family of quasi-convex, we have a quasi-convex family where each of these are in C. Okay, then the sum also belongs to C. So we have at least two classes of functions who preserve his structure with this family. Also, for the C family, there are the parallel, the Kusu differential, who was introduced also for Suzuki. And this is the definition. I don't render in details, but this is the definition of the Kusu differential. This is only for functions that are defined in Rn. Okay, so this is the Kusu differential. And he established this result. If we have two functions defining Rn to R for x and Rn, suppose that at least one of these conditions holds. Okay, this is level set strict here also, and this is the differential, no, is one or another. So in this case, the sum is quasi-convex with this differential. Now we can recuperate this result and also say anything more. Okay, so we are with these conditions. Okay, so if when Fg is a quasi-convex pair, and so the sum, then this is a quasi-convex pair, and the sum and the minimum are quasi-convex. Okay, no, I don't wait. So we can recuperate that theorem 14. This is an automatic, I don't know. So there are many other things about this work. We can talk about also the sublevel set, because the characterization of the family of the pair, we can see here the pair of quasi-convex function is related to the convexity of this union, but for time I didn't consider the book here. So with that, I finish. And there are all the references. There are many references. Okay, so thank you very much.
Thank you very much for your talk. So is there any questions from the audience? So you just unmute yourself and then ask question to our speaker. So sorry, I can't hear you. That's why I have a little bit. So I have so waiting for everyone to think about the talk. So I have some questions for you first. Yes. Yes.
Okay. I see you now. I didn't see anyone. Okay.
So I just have a question first. Sorry, I can hear my voice. So for the so you have the three categories of the pair, which is quasi-convex. So I'm just wondering that if say F1 and F2, the summation of them is quasi-convex and they are quasi-convex as well. So they necessary to fall within three cases.
Okay.
I think this is before the theorem.
Yes, this is here. Here?
Yeah, type 1, type 2, type 3. So if F1 summation with F2 is quasi-convex, and of course
Okay.
F1, F2 quasi-convex as well. So is this necessary to be type 1, type 2, or type 3?
No. This
Okay.
is these examples are to show that we can see that this is a very reduced family, but in fact it's not. No, this is not necessary.
Oh, okay.
Okay, you can have a pair, a quasi-convex pair that there is no type 1 like that, not type 2. The pair quasi-convex is more large.
Okay, then it's not type 3 as well.
No, the type 3 don't work in general. Doesn't work in general.
And I have another question regarding the result that a convex functions, if and only if this is quasi-convex under the summation with any linear functions, which is actually equivalent to T plus X star a quasi-monotone, then T is monotone.
This is the classical. Okay.
No, it is from the beginning.
Yes. This is the motivation.
Yeah, that's the motivation. Yeah, that's one. Then I'm just wondering that if we don't consider every X star belong to X star, like not consider all the linear function, but we consider the class of linear function, which is just say, for example, the linear function that has the norm is less than some constant number, something like that. And then can we use your theorem, like the main theorem, to characterize what function f, so that the this is still quasi under that summation with all the linear function, which is less than a with the norm less than a constant.
You are talking about a translation, no?
Yeah.
If you have a translation, there are always a quasi-monotone.
Yeah. So because this result means that every quasi-convex function, if it's a summation with a linear function is still quasi-convex for every linear functions, then the function must be a convex function.
Yes.
Yes. Then I'm wondering that with your main theorem, is that can this used to imply some like characterization for some quasi-convex function, which is still remain quasi with the addition with the linear function, but it's not all the linear function. It's just linear function with like say the norm less than some constant like 1 or 2 or some constant.
Okay, I understand. So you say that can see this result, but about function with our result. In general, we cannot recuperate result about monotony with our result. in this sense is very limited. We cannot use that for convexity, but we can see more or less something more weak, but I don't know now.
Okay. Yeah, thank you for your answer. And is there any question from the audience?
While we're here on this slide,
there are questions. There was earlier question from Nadia. Let's first.
So,
Nadia, you have questions?
Sorry, I just didn't want to actually interrupt anyone. So, Alex, if you have a question, then maybe I will be next after you, because we're on the right slide, okay?
So we're exercising politeness. Okay, thank you. Thank you, Yboon, for your presentation, reminding us about classical stuff, convex functions, quasi-convex functions. If you could just show the next slide, please.
The example?
Yes, this one. I'm a little bit unsure about the first equality here. This natural case, quasi-convex, G is non-decreasing. Is it really true that these two sub-level sets are equal? For instance, G is just doubling, no, 2x, something like that. I think the level set should change.
Yes, because it's not decreasing. G is not
Yes, non-increasing. For instance, G of x equals 2x.
I think the first equation should be G of lambda, no?
Yeah, I agree. G of lambda.
G of
Maybe
x,
I put something wrong here.
Yeah.
So my hypothesis, supported by the voices from the audience, is that lambda can't be the same on the left and on the right. So the idea, as far as I understand, is just to claim that the sets are both convex, but they don't have to coincide.
There are a mistake of maybe like that. I don't know. But this is like that. So, one moment. No, this is not. So because normally he is easy.
The previous one, the equality of sub-level sets.
Okay, we have this. Another one is
yes.
So if G is not decreasing, this preserve because how do you say, like this? Maybe I don't know. This is the definition, maybe, but this in this not decreasing.
These numbers definitely are equal, but I'm not sure about the level sets. If you multiply the left-hand side by 2, you must multiply the right-hand side by 2 as well.
Yeah, so it just should be G of lambda on the right-hand side in the left-hand side.
Yes, yes. But anyway, it's not important. It's just a remark. I think you wanted to claim that these two sets are convex simultaneously, but they don't have to be equal.
This is equal.
Oh, you insist.
Okay.
No, it should be. It should definitely be G of lambda in the left-hand side. Let's equal G of lambda. No.
Yeah, sure.
Here?
Yeah.
Excuse me. How do you say this and this?
Yes, these lambdas are different. It's not the same lambda. To correct the formula, as Vera suggested, you need to write g of lambda in the left-hand side of this equality.
Okay, you say that you preserve the convexity, but they are not the same lambda. Okay, understand.
I think this is what you need. You need convexity. You don't need these sets to coincide.
You need convexity, yes.
Yeah. Okay, it's just a minor remark, nothing essential. So thank you very much again for your presentation.
Yes.
I really enjoyed listening something about classical stuff like convexity, quasi-convexity, subdifferentials. Thank you.
Okay, thank you.
Nadia?
Yboon, so now I have a question. So first of all, I'm really very interested in the situation where sum of two quasi-convex functions is quasi-convex. So not very often we have it. So, but you actually provide, say, a long list of conditions, and then you have, so in this case, sum of quasi-convex functions is convex, and also minimum of these functions is also quasi-convex, right? So that's what you are saying. I just was wondering if somehow, if say sum of two, so if it happens that sum of two quasi-convex functions is quasi-convex, then the minimum is also automatically quasi-convex. So can it be actually, can one of these two be a condition for another one to be true? So minimum of two quasi-convex functions and sum of two quasi-convex functions. Just out of curiosity, I have no proof, but maybe you know the answer.
I'm sure if I understand your comment. Excuse me.
So can you, for example, say that if minimum of two quasi-convex functions is quasi-convex, then
Yes.
the sum of these two quasi-convex functions is also quasi-convex?
Yes.
You can.
If f and g are, when the functions are this is the same, okay? When we have lower semi-continuous functions, this is the same. So here we can add the sum. We can add one more item. All of that is without lower semi-continuous. We add some semi-continuous, we have this also. I don't know if this is a question.
I think the theorem is only answer another question, which is A and E equivalent to each other.
No. I don't know. Maybe she left, I think.
So I'm sorry, I'm just getting a bit confused. So the question is not about a quasi-convex pair. The question is about general quasi-convex functions, right?
That's right. So if we can avoid all the conditions for the pairs, because for the pairs, quasi-convex pair, I agree. I mean, there are quite a few conditions. I just was wondering, can we somehow substitute all these conditions by the condition that minimum of these two functions is quasi-convex? Then we have the sum is also quasi-convex instead of taking all the conditions for the pairs.
Okay, I now understand. I don't know, but I don't know the answer. Okay, I understand the question now. Okay.
I have a question, Yboon. Thanks for the presentation. It was really quite enjoyable and very, very nice. Suppose you have 3 functions,
Okay.
and each are pairwise a quasi-convex pair.
Mhm.
Do they form a quasi-convex family?
Yes, we have I present only part of the result. In general, we have a result from a family of.
Yeah. So
this
if you
family.
have,
This is only for 2, but the general result is for
yeah.
a number in
So
general can be
if
infinite.
F1 and F2 are a quasi-convex pair,
Yes.
and F2 and F3 are also a quasi-convex pair,
Yes.
then can you conclude that F1 and F3 is a quasi-convex pair?
Yes. Yes.
Okay,
I
thank
have
you.
a question on top of Julian question. So isn't that you have a result saying that the quasi-subdifferential of the function had to be contain the other subdifferential of other function. So which means that they pairwise contain each other. So
Container is not exactly, it's like this. The condition is like that. Is equal in general. Okay, this like the condition is like this. This is the congenere of the differential. One is containing another one, or of course the other. One of these. This is a condition. No, this is not equal. This is contained. This is a general con. Maybe that. This is a type 3, the type 1.
So I mean, just so the subdifferential of the sum of the function is gonna be the sum of the subdifferential, still, right? For quasi subdifferential, then probably we still have then the one subdifferential will contain the in the subdifferential of the sum of the 2 functions. So that answer Julian question.
You talk about that?
Yeah.
Okay.
So that is equal subdifferential of f plus g.
Like that?
Yeah.
No, we have anything. No, we don't have condition for that.
We don't have that. Oh.
No.
Okay.
This is too much. No. We can take some condition if you like this. This no. But maybe like this, yes. Only is with that. If you can find something will be like that. Always when we work with convexity, quasi-convexity, excuse me, there are all like, this is like a relation of con. This is like generate, no? You have a set and you generate a con. So this is, you can obtain something like that, but no only with the differentials. At least that is a particular case, but in general, no.
Okay, thank you.
Just a comment that this is very useful already, right? Because that should allow you to calculate like directions of descent and things like this, right? So it's
Yes, when we work with quasi-convexity or with quasi-monotony, we are interested in direction, all time in direction. Yes.
Okay, so is there any other questions from Nadia or the audience? Okay.
no more questions. It's just a very enjoyable talk. I have learned a lot about quasi-convex functions.
Yeah. So,
Excuse me for don't understand some question.
yeah, I think that if there is no other questions from the audience, so please join me to thank Yboon for her very interesting talk. So please